Yes, I'm in a different place now. You can see the different light and settings. Hopefully, you're just looking at the screen with the lectures and not me. But anyways, as students have suggested, aesthetics matter, right? So we are on to chapter 8, where we are going to look at climate and its impacts on vector-borne and zoonotic diseases. I think everybody understands these terminologies. Vectors can be insects like mosquitoes or ticks, and zoonotic also means they are jumping from animals to humans, birds to humans, right? So we will see some examples. Immediately, we want to set the stage. When we want to look for climate connections, often there are empirical relations that people look for: temperature increase and increases in incidences of a certain disease, or changes in precipitation. But we will see that the stories are always much more complicated. Finding the actual climate connection to disease outcomes through all the links in between in terms of population of vectors, phenology, life cycle of vectors, so droughts versus floods, and how mosquito populations are affected versus how human exposures are affected. They all get pretty complicated. So as a list, we can say microbial adaptation and change matters. Human susceptibility to infection itself is always a key factor. Climate and weather, of course, is what we are focused on here. Changing ecosystems, so droughts and floods affect vegetation very differently, and water puddles, standing waters, human congregation towards water, birds coming towards water, everything changes, right? Changing ecosystems, so how different species respond to climate and weather also matter. Economic development and land use, so deforestation, conversion to agriculture, urbanization, those sorts of things matter. Human demographics and behavior, so forced migrations, climate-related migrations, El Nino-driven changes in demographics and so on contribute to the disease emergence. Technology and industry, of course, that can be in various ways: air quality, water quality, or just technology in terms of transportation, or technology in terms of medical treatments, access to care, and so on. Vulnerability and risks. International travel and commerce, as we saw with COVID and other diseases before, like SARS, bird flu, and so on. People fly around and go into regions where they get into new diseases they are not exposed to, or they bring new diseases into regions where people are not immune to, and so on. Breakdown of public health measures, so extreme events are causing a lot of these things, especially cyclones, floods, and so on. Poverty and social inequalities. We talked about physical and social vulnerability, so we will have to remember that also in terms of deciding the ultimate disease emergence. War and famine, forced migrations, and unhygienic conditions, lack of sanitation, water treatment, etc. Lack of political will to take action. Many of the COVID responses in several countries have been called into question about the political will to deal with the pandemic because of considerations for economic issues rather than health issues. Intent to harm, so it can be like bioterrorism, or just subjecting one particular section of the population to harm because of electoral or political considerations, and so on. Okay, so we will look for this model called convergence model for emerging diseases. That gives you a sense by the end that while climate is an overriding factor, it's a force multiplier, and it's obviously providing the environmental conditions for pathogens, humans, ecological factors, and affecting genetical and biological factors. Ultimately, social, political, and economic factors, as well as physical environmental factors, come together with what the microbes will do in response to these changes to give us the emergence of diseases. So finding the just the climate factors, which is our focus here, is not always very straightforward. There are many steps to go from climate and weather forcing to all these factors and then the ultimate disease outcome. Okay, we have to keep that in mind. I won't mention the adaptation strategies in each case. The book kind of mentions them not in a very systematic way, but you can imagine that each time reducing risk by reducing the exposure, by disease preparedness and early warning systems and so on are always key factors, but social, political and economic factors also play a big role. Okay, in addition to genetic and biological factors. So keep that in mind as we go forward. And we are now also getting better at these sorts of things, where these are the number of months per year when disease transmission by Aedes aegypti mosquito is possible. So here you are looking at the number of months, 1 to 12. And we are starting in 2019, looking at a snapshot of 2050 and 2080. These are, of course, model-based projections, and current is an estimate, but still modeled. So you have to be always aware of that. As we said before, 2050 and 2080 have lots of scenarios built in to them in terms of land use change, population, socioeconomics, renewable energy considerations, transportation changes, agricultural changes, and so on and so forth, maybe even carbon capture and sequestration included, etc. But nonetheless, you see what we expect with warming and precipitation changes. So just look at it a few times. So 2019, you are starting with this map, and as you go into the future, the number of months with disease transmission possible is going into higher and higher latitudes, which intuitively makes sense, but you can see that they are shrinking here. For example, if you look at some of these low latitude regions, the precipitation change, especially in the Sahel region, which is the transition between the rain and the desert, and there are many other regions where the mosquito model produces changes into the future which show a reduced number of months, but that's not always necessarily just a positive thing, because it may come with food security issues, nutrition issues, and so on. So one has to remember all those sorts of details. These are the kind of diseases we will consider. So vector-borne and zoonotic diseases. Lyme, we'll look at will not look at necessarily encephalitis, Rift Valley fever, plague, tularemia. We will look at West Nile. We will not look at all these others. We will look at malaria, dengue. We will look at rabies. We will look at let's see, we will not look at hemorrhagic fever and so on. But these are the broad range of vector-borne and zoonotic diseases that are of importance when we consider climate and vector-borne and zoonotic diseases, which are referred to as VBZDs, vector-borne and zoonotic diseases. These are the pathogens. We will consider some of them, but we have to consider in detail the response of the pathogens themselves and their hosts and their life cycle, whether they can reproduce in the environment or they always reproduce in the hosts, and then how the host phenology will change, their migrations, and how the pathogen itself will change. So here are the various vectors. We will look at several mosquitoes and some ticks and some not necessarily rodents, but we will consider vampire bat, for example, in the case of rabies and so on. But you see the idea. You have deer, mouse, rodents, livestock, birds, mammals, humans themselves can be hosts as well. Then what do we have? Rodent species on land, Egyptian fruit bats, and so on and so forth. So let me stop here and come to the next podcast in terms of the other details of what we need to worry about when we talk about climate change and vector-borne and zoonotic diseases. Okay. Just keep in mind that we are not going to connect the dots all the way from climate and weather to disease outcome, but we will raise all the critical issues that we have to worry about, so that when we do planetary health, adaptation mitigation measures, and disease preparedness, process understanding to build early warning systems and so on, all these links will be needed. Sometimes models can work as engineering approaches by finding empirical relations between habitats and pathogens, or habitats and vectors and hosts, and still provide critical information for disease preparedness. That's sometimes the goal. Okay.